Hey, thanks for tuning in. Welcome to Nomadic Geek. Do you want to be able to steer your ESP32-CAM surveillance camera up and down like this? Or steer the wheels of a robot with an ESP32 powered module? Then you have to see this video to the end, as we are going to show you how to steer your camera from your dashboard on any Wi-Fi capable device you want. Your smartphone, PC, anything that has a web browser will do. So let's get started. Let us first take a look at what we need for this tutorial. I will be using the Freenove ESP32 rover module, but the ESP32-CAM will also work, as well as any other ESP32 powered board. The reason why I'm using the Freenove version is for its ease of use, as well as the number of exposed GPIOs. To control a stepper motor, we will need at least one pin for each coil. We also, of course, need a stepper motor with its corresponding stepper driver. The stepper motor used in this tutorial is the 28BYJ48 with its ULN 2003 base driver board. The motor is a 5-wire unipolar stepper motor that runs on 5 volt. It has a step angle of 5.625 degrees through 64 and provides good torque even at a standstill. The driver board consists of 7 Darlington transistor pairs, with 4 pairs used in this setup. It has 4 control inputs and a power supply connection, allowing it to drive a load of up to 500 milliamperes and 50 volt. Last but not least, the Arduino IDE and any other IDE that you prefer for the Node.js server. Please hit the like button, subscribe, and notification bell. It would help me greatly with the algorithm so that I can find motivation to keep delivering tutorials like this. I would also appreciate it if you could provide feedback in the comment section. Now that we have gotten that out of the way, let's dive in and start controlling the motor. First, we are going to write the code for the ESP32 powered CAM module. We will set up a WebSocket client on the ESP32 board and listens for messages from a WebSocket server. It will also control a flashlight and a stepper motor based on the messages it receives. Additionally, it initializes the camera configuration settings for capturing and streaming video to a Node.js server. We start by including several libraries, including one called secrets.h that contains sensitive data such as Wi-Fi network name and password. This block of code also incorporates various libraries required to operate an ESP camera module and establish a connection to Wi-Fi. Specifically, it includes the ESP_camera library, which grants access to the camera, the Wi-Fi library, which facilitates connection to a wireless network, the Arduino WebSockets library, which enables communication via WebSockets. Furthermore, it includes camera_pins.h, which contains certain definitions tailored to the camera module being employed. Collectively, these libraries empower the ESP to capture images and transmit them over the network via WebSockets. I am using the Rover Kit camera, which is the one for the Freenove module. If you are using an ESP32-CAM module, yours is most probably the AI Thinker one. In this block of code, we see 5 different pins being defined with the hashtag define statement. The pins are used to control different components of a device or a project. Specifically, the pins are being used to control the stepper motor and an onboard LED. The stepper motor is controlled using 4 different pins, stepper_pin_1, 2, 3, and 4. The LED is controlled using the flash_pin. It's important to note that we're using the flash_pin variable to control the LED on pin 2 of the Freenove rover module, as this module does not have a flash LED like the ESP32-CAM module. If you're using an ESP32-CAM module and want to control the flashlight, you can use GPIO pin number 4 instead. By defining these pins, the program can easily refer to them by their names instead of having to remember the specific number or location of the pins on the microcontroller. In this block of code, we see several variables being defined. The first 2, SSID, and password are used to store the name and password of the Wi-Fi network that our device will connect to. If you want to keep this sensitive information separate from your main code, you can define these variables in a separate secrets.h file and include it in your code instead. If you want to learn how to do this, you can watch my short instructional video in the description or click the card on the screen now. The next two variables, WebSocket server host and WebSocket server port, define the IP address and port number of the WebSocket server that our device will connect to in order to send the captured images, as well as our commands data. These variables will be used further down in our code. If you don't want to use a separate secrets.h file, you can also set the SSID and password variables directly in this code. Just replace network_name and password respectively with your Wi-Fi network name and password. Similarly, you can also update the WebSocket server host and WebSocket server port variables to the appropriate values for your project. The port number will be used by the Node.js server to differentiate between the different sensors and devices, and the host will be the IP address to the computer hosting the Node.js server itself. If you want to learn how to check your server's IP address, you can watch my short instructional video in the description or click the card on the screen now. This block of code defines two variables, flashlight and steps. The variable flashlight is set to 0, indicating that the flashlight, or in my case, blue LED, is currently turned off. The variable steps is set to 40, which specifies the number of steps that the stepper motor will take in each direction for each message received from the Node.js server. These messages are controlled by the user through a web browser GUI, which displays a dashboard for controlling the device. These variables will be utilized and further explained later in the code to regulate the flashlight and the stepper motor according to the user's input. Here, we are utilizing the WebSockets library to establish a connection with a server using the WebSockets client class. The connection will be used to transmit and receive data in real time. The variable client is an instance of the WebSockets client class. We are also declaring a structure variable config with the type camera config t. This variable is used to store configuration settings for the camera module, which will be used later in the code. This block of code defines a function called onEventsCallback that will be called by the WebSockets library when certain events occur. Specifically, this function is called when the WebSocket connection is opened or closed. If the event is a connection opened event, the function will print connection opened to the serial monitor. If the event is a connection closed event, the function will print connection closed and then restart the ESP32 using the ESP.restart function. Restarting the module helps clear memory and ensures that the setup function is executed again, which waits for a connection to the Node.js server to be established again, which we will see further down in the code. If you want to learn about the Arduino lifecycle, you can watch my short instructional video in the description or click the card on the screen now. This is a function called onMessageCallback, which will be called whenever a message is received from the Node.js server. The message is passed to the function as a parameter. Inside the function, the message data is extracted using the data method of the message object and stored in a string variable called data. Then, the code searches for the index of the equal sign in the data string using the index of method, which returns the position of the equal sign. If the equal sign is found, the code extracts the key and value parts of the message using the substring method and stores them in separate string variables. The key is used to determine what action to take, and the value is used to determine the specific parameters for that action. For example, if the key is on_board_LED_1, the value is checked to see if it is equal to 1. If it is, the variable flashlight is set to 1, indicating that the flashlight should be turned on, and the pin connected to the flashlight LED is set to high using the digital write method. If the value is not 1, the flashlight is turned off and the pin is set to low. If the key is motor_forward, the forward function is called, which moves the stepper motor forward. If the key is motor_backward, the backward function is called, which moves the stepper motor backward, which we will find further down the code. Finally, the key and value are printed to the serial monitor for debugging purposes. This function initializes the camera configuration settings for the camera module. The settings include LEDC channel and timer, and pins for various data lines such as D0, D1, and so on. It also specifies pins for external clock, pixel clock, vertical and horizontal synchronization signal, and I2² serial and clock. Additionally, it sets the frequency of external clock to 20 million Hz and the frame size to quarter video graphics array. The pixel format is set to JPEG for streaming purposes, but it can also be set to RGB 565 for face detection. The grab mode is set to camera grab when empty, and the location of the frame buffer is set to camera FB and PSRAM. Finally, the JPEG quality is set to 12, and the number of frame buffers is set to 1. It's worth noting that these configurations can be adjusted to fit specific needs, such as changing the frame size or pixel format. The JPEG quality can also be adjusted to optimize the performance of the system. Overall, adjusting these configurations can optimize the system's performance without sacrificing image quality. If you are using the ESP32-CAM module, this config may differ a bit. You can use the config used in the examples code for your module. If you don't know how to install your board in the Arduino IDE and check the example codes for it, you can watch my short instructional video in the description or click the card on the screen now. This is the forward function. The function uses two for loops to execute the sequence of movements required for the motor to move forward by the specified number of steps. The number of steps is defined by the steps variable, which we saw was declared globally further up in the code. Within the loops, there is a switch statement that determines the state of the 4 output pins connected to the stepper motor. Depending on the value of variable I in the loop, the switch statement sets the appropriate combination of output pin states to produce the desired movement of the stepper motor. For example, when I is 0, the switch statement sets the first output pin to high and the other 3 output pins to low. This causes the stepper motor to move 1 step in a certain direction. When I is 1, the second output pin is set to high, and the first output pin is set to low, causing the motor to move 1 more step in the same direction. This pattern continues until I reaches 3, at which point the 4th output pin is set to high, and the other 3 output pins are set to low, causing the motor to move 1 more step in the same direction. After each combination of output pin states is set, the function waits for a brief period of time using the delay function before continuing to the next iteration of the inner for loop. This delay is necessary to ensure that the motor has enough time to complete each step before the next step is executed. If you would like me to create an in-depth tutorial on how the stepper motor works and why we are controlling it in this particular way, please leave a comment below requesting so. This function does the same thing but turning the motor backwards instead of forward, so let's continue further down. This is the setup function for the program. It begins by initializing the serial port to communicate with the computer at a baud rate of 115,200. Next, it calls the CAM-CONF-init function, which we previously discussed, to set up the camera configuration settings. It then initializes the camera by calling ESP32-CAM function with the configuration settings as an argument. After initializing the camera, the code retrieves the camera sensor's properties with ESP32-CAM-sensor-get function. It then sets the contrast to 0, turns on the raw gamma mode, and flips the image vertically using the set contrast, set raw GMA, and set flip functions, respectively. So if your images captured are upside down, this is where you can change it. The code then proceeds to connect to the Wi-Fi network by calling Wi-Fi begin function, where SSID and password are the name and password of the network, respectively. This is where the SSID and password variables, which we defined earlier in the code, are used. The code waits for the Wi-Fi connection to be established by checking the status with Wi-Fi status function and delays for 500 milliseconds until the connection is established. Next, we set the output pins for the LED flash and stepper motor using the pin mode function. This is where the variables for the flash pin and stepper motor pins are used, which we defined earlier in the code. Moving on, We set up the WebSocket client by defining callback functions with client.onMessage and client.onEvent. These functions were defined earlier in the code and are now being used to set up the WebSocket client. The code then enters a while loop that attempts to connect to the WebSocket server with the client.connect function. The loop delays for 500 milliseconds between attempts until the connection is established. Once the setup function has completed, the program will move on to the loop function. In the Arduino lifecycle, both the setup function and loop function is required. The loop function is a function that runs continuously once the setup function completes its execution. The loop function is responsible for the main logic of the program, and it runs over and over until the Arduino is powered off or reset, and is considered the heartbeat of the Arduino program. So the loop function is responsible for performing any tasks that need to be repeated over and over, such as reading sensors, updating outputs, and checking for input events. The first line of the loop function, the client.poll function, is used to check for any incoming messages or events from the WebSocket server. This function checks the WebSocket connection and listens for incoming data. If there is an incoming message, the client.onMessage is triggered and the onMessageCallback function is executed, which handles the message properly. Next, the ESP-camera FB get function captures an image from the camera and stores it in a camera FBT structure. If no image is captured, the function returns null and the program continues to the next iteration of the loop. If an image is captured, the image data is sent to the WebSocket server using the client.send binary function. The image data is sent as a binary array. After sending the image data, the ESP-camera FB return function is used to free the memory previously used by the camera FBT structure. Finally, the program sends a message to the WebSocket server containing the status of the LED using the client.send function. This message includes a string on _board_LED_1 equals concatenated with the current status of the LED. The loop function continues to run heartbeat by heartbeat until the program is stopped or reset. The next step is to upload the code to the ESP32-based board. If you are using the Freenove module, as I am, simply push the upload button, provided that you have selected the correct board in the Tools menu. If you are using the ESP32-CAM module and don't know how to upload the code, you can watch my short instructional video in the description or click the card on the screen now. Server, you may use the Integrated Development Environment (IDE) of your preference, but in this video, I am demonstrating the use of Visual Studio Code (VS Code). Here we have our project. We have a file explorer located on the left side, where all of our project files are stored. It consists of a public folder which holds all the files that are accessible from the client side. Then we have our package.json, which contains important information about the project, such as scripts and version numbers, amongst others, and is necessary for using npm, the package manager for Node.js. And lastly, the server.js, which is the core of our project, where all the server-side logic and functionality are defined and implemented. As you can see, I have the package.json file open. When you initialize a Node.js project with npm in it, the package.json file is automatically created and provides you with the opportunity to specify important details such as the name, author, description, and more for your project. You can always modify these details later on within this file. If you need instructions on how to create a project from scratch this way, you can either click the card on the screen or find a link to the short instructional video in the description after watching this video. These are the dependencies that the project is using. Express is a fast, minimalist web framework for Node.js. It provides a lot of the functionality needed for a web application, including routing and middleware, and makes it easier to build a server. The Path module provides utilities for working with file and directory paths in Node.js. It allows you to manipulate file paths in a way that is platform independent, so you can write code that works the same on Windows, Mac OS, and Linux. The WS module provides a WebSocket implementation. WebSockets allow real-time communication between a server and client, and are commonly used for things like chat applications and online games. The WS module provides a simple way to work with WebSockets in Node.js. To install a dependency, you can use the Node Package Manager command line tool. The npm tool is installed with Node.js and can be used to install packages from the npm registry. If you need instructions on how to install Node.js and its package manager, you can either click the card on the screen or find a link to the short instructional video in the description after watching this video. The script section of our package.json file in Node.js defines command line scripts that can be run using npm. In this specific case, we have two scripts defined. Test. This script is supposed to run tests for your application, but as the script itself says, it just returns an error message indicating that no test is specified. Start. This script is more important and is used to start the server. It specifies that when the command npm start is run, the script should run the server.js file using the node command. These scripts can be run from the command line by running npm run script name. For example, to start the server, you would run npm run start. In this tutorial, I shall only address the modifications made since the previous video. Should you desire an in-depth understanding of the code, the antecedent video can be viewed by clicking on the card displayed on the screen. I have appended a fresh device object titled Motor Unit on port 8887 to chart the device we have just uploaded. It incorporates two commands, one for steering the motor forward and the other for steering it backward. The IDs correspond to the commands in our Arduino code. Additionally, we have assigned labels and CSS classes to them to associate the appropriate icons with the buttons on the dashboard GUI. There is nothing new for the client code. We are processing the sent commands in precisely the same manner as in the previous videos. The same for the device's code really. In the clients.js file, we have made a few alterations. The dashboard cards are rendered out as usual, but the command buttons must be added for each card. Thus, we add the button for each card and attach a mouse down event listener to it. When a button is held down, such as the motor forward button, the client transmits the command to the server every 100 milliseconds using the JavaScript setInterval function. To make the setInterval function stop when releasing the button, we also need a mouseup event whose sole purpose is to clear the interval timer. This stops the timer, which in turn stops the messaging to the server, effectively halting the motor movement. For the CSS, we only need to add the two classes assigned to the device object, forward icon and backward icon. We are using one and the same SVG file for both classes and rotating it for the backward class. The up.svg looks like this. Now, all that remains is to test everything together. In the serial monitor, we can see that the module restarts upon connection closure. Once we start the server again, the ESP32 powered board establishes the connection with the Node.js server. I reload the client, even though it is not necessary, and we can see the commands being sent from the client rapidly appearing in the Node.js console and the serial monitor, which is monitoring the execution of the ESP32. If you enjoyed what you saw, make sure to hit the subscribe button and give this video a big like. That way, you'll never miss a single one of my future uploads. And if you have any ideas for topics you'd like to see me cover in the future, drop a comment below. Your feedback and suggestions are always appreciated. So until next time, farewell and keep on learning.